Good afternoon. My name is Tomas Vivanco. I'm assistant professor of the Faculty of Architecture, Design and Urban Studies of the Pontifical Catholic University in Chile. Also a PhD candidate of Digital Futures in Tonji University. Today, I will present our research based on 4D printing, computational mechanical design of three-dimensional 3D printed patterns over tension textiles for low energy three-dimensional volumes. From the distribution of the embedded energy materials, they can be operated in order to design and produce optimized material systems with minimum use of external energy to achieve its maximum three-dimensional capacity within their mechanical constraints. This research studies the process of 3D printing bidimensional layers over a pre-tensioned fabric to generate three-dimensional shapes. After the tension of the fabric is released, the printed pattern generates tension and compression over the textiles, which conduce and distribute the internal forces, generating a controlled deformation with a final form. Digital simulation of finite anticlastic shapes and parametric design under mechanical constraints of the material are used to predict and compare both physical and digital forms. This allows us to evaluate and optimize the printed pattern in order to decrease the amount of used energy and materials to produce a performative shape. This research initiates by the very basic observation. A cube of ice is an individuality in defined environments where it can resist some variations without losing its own identity. Nevertheless, if the environmental change too much, the ice will dissolve. This means that the cube of ice can resist, but it can't change its environment. The transition from an individual material to an entity lays on its capacity of establish a dialogue in between the object and its transformation. The complexity of a material and its capacity of anticipation or prediction to its environment or mechanical changes are similar with the uncertainty of the environment with the capacity of changing. Materials computation doesn't require the use of computers. To compute physical forms, computational tools might be needed to explore, evaluate, and simulate formal behavioral and mechanical properties of the potential outcomes. Understanding and controlling the distributed forces of different materials allows computing its mechanical and formal behaviors, pursuing performativity. Formal reactions, transitions, and variations led by the information embedded in materials are conditioned to environmental, structural, and mechanical constraints that affect matter in different interactions, giving it a gradient continuity, promoting heterogeneity and fluidity instead of rigid and static development. A material entity embeds its material characteristics, geometric behavior, and manufacturing processes by integrating a wide understanding of form, structure, and behavior. By activating the information of material through mechanical stimuli, such as stretching, new formal compositions can be explored under the condition of physical and mechanical constraints. These activated forms can be stabilized by the use of a second material or element, achieving an equilibrium state of the tension, allowing to decrease the amount of energy invested into the configuration of three-dimensional forms by operating the material in two dimensions. In this case, the use of horizontal forces to create vertical deformations. Previous studies in three-dimensional behavior of the bidimensional patterns to create 3D forms by applying a resin pattern over pre-stretched textiles were done by Oxman and Rosenberg, have led to the development of digital simulators to study the relationship between geometry and material behaviors in both digital and physical prototypes, defining the transitional process of a bidimensional to the three-dimensional form as four-dimensional, due to the self but controlled material changes, in this case, the latex jet. Also, research developed by the Self-Assembly Lab at MIT and by Nervous System were both experimenting with forming structure of over pre-stretched fabrics. This raises the main question for us, that the concept of operating materials through the information raises the question of which could be the minimum energy, understood as information or material, investing to maximize three-dimensional performativity. At the same time, how much control of the physical final form could be achieved and how the mechanical constraints can be incorporated into the design and digital production process to predict the outcome. The aim of this research is to study both physical and digital prototypes through the development of a simulator tool that predicts three-dimensional forms working only in two dimensions in order to create the amount, in order to decrease the amount of energy invested. The main function of the simulator is in first instance to predict the resultant three-dimensional shapes designed in two dimensions. In a second instance is to study the reflection, digital and physical prototypes, and at last to compare both physical and digital prototypes. The design methodology developed in this research is primarily divided into 5 steps. The first step is to define the input pattern by finding studies using physical prototypes with both analog and digital fabrication processes. Second, the application of the material theory of pattern columns. Third, the development of a digital simulator that makes visible an approximation to the form generated from the input pattern and the output form. Fourth, the generation of the physical outcome. And fifth, the mechanical analysis of both digital and physical outcomes. A critical step for the detection of patterns and discoveries will serve for further developments. The input pattern, as an elastic membrane, is horizontal prestage to distribute force, which creates a volume once it's released. The input pattern is a stiff flat geometry that will work in compression when the tension is released. Through this, the membrane will contract to generate a three-dimensional deformation. First prototypes were done with latex sheets and epoxy resin patterns. By the end of this test, 2 issues stood out. The first, a large amount of time invested in the preparation of the materials to test the prototypes, and second, that the latex sheets weren't homogeneous in their height and size, making the prototypes not comparable with others. In order to have standardized measurements of the former latex sheets, were replaced by elastic textiles. Also, a form finding process led to define basic patterns, geometries, crosses, squares, circles, and parallel lines with different width and orientations over the tension of the fabric, where the density and rigidity of the resin played a key role in setting the final shape due to the compression stress which is subjected, considering a pre-stage length of 50% of the textile sheet size was considered for the development of the initial prototypes. Based on the previous step, 3D printed basic patterns with precise control over the printing variables of thickness, linearity, and height of the input form needed to be defined. Initial forms are generated to contrast or validate the behavior of the previous prototypes. The similar to the Young's model in textile engineering is the compression between the stretching of the fabric with the force applied to stretch it. It's understood as the comparison between the stress and the strain of the material. Specifically, Lycra DuPont can be stretched up to 100% of its sides in one direction, but in the other direction, it can only be stretched 75% of its sides due to its fiber directions. This defines a stretch length criteria to considering its most unfavorable elasticity of the size of its sheet. Conditioned by the freedom of the ends of the column defined as a pivot, fixed or free, the bending columns theory is based on the solution of the differential bending moment equilibrium. PCR in this formula, in the last formula shown above, PCR is called critical bending pressure that becomes relevant for design since it determines the material to be used and the wanted deformation related to flexural rigidity and the cross-sectional area of inertia, respectively. Compared with the central buckling equation, it can be noticed that its theoretical value will only describe the column's behavior when the bending pressure is equal to P, CR. Thus, for higher or lower values, the bending equilibrium will be present only if the column remains with no external pressure perturbations, except the bending pressure. Given this explanation, it is possible to contrast the deformation of the 3D printings in Lycra through the end parameter, that's the buckling mode, that will define the number of curves that the printed figures will have when the textile is released. Through the static study of the columns, a specific combination of extremes are analyzed for their structural relevance and their mechanical feasibility. Understanding the key properties of the materials that give structure and form of the prototype, deformation of 10 were compared with the deformation curves named above. An adapt column buckling theory was used to predict the forms that were printed and then compared. Initially, to mechanically simulate the static condition of the prototypes, the base geometry of the membrane and input pattern were parameterized and the fixed vertices from the flat parametric surface were extracted. From this initial setup, a 5-step computational definition was made. The guiding key of the form finding process within the simulator is the assignation of mechanical reactions to each anchor point in the input pattern, similar to the reactions that we'll have in a physical prototype. Based on initial prototypes, it was observed that there are mainly 3 types of Lycra bonds: fixed, hinge, and free, since their mechanical behavior was relatable to the column buckling theory. This combination will generate a deformation in the simulator. Considering that the pivot type support generates parallel and perpendicular reactions, the fixed support generates the same reaction as the fixed one, added to moment of torsion reactions towards the center of the bar. The 3 supports generate the reactions only on the axis towards which it is an external force applied. By varying the height of the 2 of the sides of a square printed pattern, the final outcome was deformed in only one direction. That's in the image, the T prototypes. Even more, when segmenting the length of the pattern and giving each section a different height, thinner parts had a lower resistance to compression, a greater deflection and deformation of the output physical form. The geometrical interaction between the textile tensile stress and the input from generated variable control outcomes that allows to pursue a functional final form. The development of a functional prototype was possible due to the incorporation of the different behaviors of C and T prototypes mentioned above, making possible to predict the outcome form and its geometrical assimilation of the input figure. Printed pattern works as a continuous and closed geometry under the mechanical principle of deflected buckled columns, transmitting forces between them until they achieve a static equilibrium. Depending on the height and/or the segment of the trace, the energy will distribute until it finds its own stiffness balance. As shown in the image, the deflection principle finds its own equilibrium by distributing forces all across the fabric, generating a deformation and a resultant geometry. With the accurate printing over the textiles, the outcome physical prototype will be structurally adapted, keeping a force balance similar to the simulator form. For the development of the outcome prototypes, the tension input shape, thickness and height of the print, and the number of hinge of segments of variation in height of the figure were varied to influence the performance of the outcome relatable to critical pressure and inertia in theory of columns buckling. As shown in previous prototypes, this research reveals that by segmenting the printed bidimensional input pattern length in its three-dimensional achievement can increase considerably. This change of thickness and hinge gives a better resolution and control over the outcome physical form, opening new exploration for design considering angle changes and straight elements, as shown in initial further developments. developing an integrated research between physical and digital prototypes based on mechanical constraints. Material strength can be considerably be optimized through the geometry, decreasing the amount of embedded required energy of three-dimensional forms. The input pattern through the force of the textile controls and adapts the embedded energy generated and actuated transformation from a bidimensional to a three-dimensional form defined as four-dimensional. Thank you very much for being listening my presentation. Please, if you have further questions, contact me through my email or my Twitter or social networks. Thank you very much.